Но это ложь. Я не буду читать лекцию на русском, потому что будет даже хуже вам, чем мне. So I don't remember the exact title, something like adelic decompositions. But I myself was always intimidated by these. So I want to spend some time motivating similar constructions in a context that mathematical physicists are familiar with, perhaps. Vector bundles via so-called solid algebraic geometry. So the main goal of this talk is to motivate and explain what this is. It's a generalization of algebraic geometry that works well when you have to deal with topological vector spaces. So this theory is originally due to Clausen-Scholze as part of a larger program to do analytic geometry. But this part of it works very well just for algebraic geometry and for the kinds of objects that appear in certain approaches to things like correspondence. So I'm going to start with that.
So you want something infinite dimensional?
Something infinite dimensional, but then we'll come back down to finite dimension. So it's actually partly about the interplay between infinite and finite dimensions. So I'm going to introduce V. This is just ring a formal Laurent series in some variable Z. K here, K will be just a field, but I want to emphasize it's a discrete field. And then all of the topology will be in the variables. So I could write C, but I would want to think of it as a discrete field, and that's confusing, so I'm just going to write K.
So K cannot be C.
It can be C, but you have to consider C as a discrete field. So I'm going to do algebraic geometry rather than complex analysis. So for C as a discrete field, it might as well just be any uncountable algebraically closed field at characteristic 0. It's not important. Okay. So you can write formal Laurent series as a union by order of pole. So I have a power series part and then some order of the pole. So I'll call these VNs. And the exposition for this part, I'm following a paper of Motohiko Mulase about algebraic approach to solitons. But the original version of the theory, I think, is due to Krichever and Mumford and then Sopper. So we're going to consider this as a topological vector space, where power series, you just think of it with the product topology, coefficient by coefficient, and then I take the union over all of those, so these form a basis of open neighborhoods of 0. And I want to consider in here closed subspaces. W in V, and then I want to consider the projection onto V mod V to the n, Vn. And I'm going to call this map, need to give it a name, let me call it gamma, depends on n and on W. So it's a map from some closed vector space onto this quotient. And there's a condition that you impose on W, which is that this map be Fredholm, in the sense that the kernel and cokernel are finite dimensional. So if you look in Presley and Siegel's books on loop groups, this would be some kind of Hilbert space with a splitting into positive and negative, and then you would be looking at some kind of operators that were Fredholm of this sort. So this is the algebraic geometric version of that. So you assume that this is Fredholm, and so it has an index. The index will be called mu. So this is dimension of kernel. Over the ground field minus dimension of the cokernel. And then such subspaces, it turns out, form the points of some kind of infinite dimensional Grassmannian called the Sato Grassmannian. So at the level of points, a piece of the Sato Grassmannian of, it's called index mu level n so this is a closed Fredholm subspace. It's Fredholm in this sense. Where this Fredholm operator has index. And all of these together, you have to kind of figure out how to parameterize objects of this and put charts on it, but they form some kind of infinite dimensional scheme called the Sato Grassmannian. And, well, Presley and Siegel and Sato, they formulated the KP hierarchy as some kind of flow on this Grassmannian. So you can study KP hierarchy as some flow on this infinite dimensional variety. And you should be a little careful.
Sorry, when you write the union of
yeah, so
unions, they are related for some pairs of unions.
Yeah. So no, this is a disjoint union. So this has many connected components. I just told you what it is as a set. The actual structure of it as some kind of infinite dimensional variety is not important for everyone to want to say. I'm actually going to be focusing on the data that appear as points here and explaining where they come from in algebraic geometry. So if you want to study the geometry of this thing, be a little careful. I was trying to read about this. And when you try to search for Sato Grassmannian, you get 100 papers, which are not about this thing. They're about something else. So there are kind of two things that people call Sato Grassmannian. And Drinfeld, who's very clever, calls the other one that everyone writes about the co-Sato Grassmannian. This is what I mean. Okay.
But Segal and Wilson is about that.
It's about this, and they also study the other ones, but they study them in kind of dense subspaces of this one. So they introduce a whole bunch of dense subspaces corresponding to different kind of regularity conditions and functions. Okay. So this is, I just want to treat it as some kind of linear algebraic data. I'm advertising that it has some infinite dimensional geometry, but I want to explain where this data comes up in a concrete problem. So this is the so-called Krichever correspondence. So this is a correspondence between three kinds of data. There's going to be algebro-geometric data. There will be linear algebraic data formulated in terms of this. And then there's some kind of differential equation data. So it's just some kind of commutative ring of ordinary differential operators in one variable. So this satisfies some condition. The kind of non-triviality condition. And the correspondence is that there's some natural constructive relation between all of these things. So what appears in the geometric data will be a curve. I'll just write down symbols, and then over there I'll tell you exactly what the data is. So there's a curve, there's a point on the curve, there's a vector bundle, more generally some torsion-free sheaf, and there's some map. This is some kind of formal coordinate. And there's some other map, which is some kind of trivialization data for f around P. And the linear algebra data will involve, in particular, one of these W's, but also some subalgebra here that stabilizes it. So this will be, it has to be non-trivial, bigger than just the scalars. So that actually will put a condition on W. So this will be some non-trivial subalgebra. Stabilizing W. So if I act on W as a subspace of here is preserved. And the theorem is that there's some constructive correspondence between all of this data, matching up some numerical invariance. There's a notion of index, level, and rank for all of this data. And
sorry, should we think about Z as about the local coordinate?
Z will come from a local coordinate on some ramified cover around P. So that's what, I'm going to say exactly what P is, and then we'll see the coordinate appear. And what I want to focus on is this direction, because in the construction in this direction, I will see the kind of data that I'm interested in for many other reasons as well. So I'm not going to tell you anything about the Krichever correspondence that experts don't already know, because I have nothing new to say, but this is a context in which the kind of constructions that I want to generalize appear natural. Okay, so what exactly is this data? Let me give a definition. So for the purposes of this talk, a geometric data for the purposes of this Krichever correspondence is, so it's a C is, it's an integral. You can assume smooth, but it's interesting in applications maybe to allow some singular point somewhere. So it's an integral projective curve. P in C is a smooth point. It will actually appear as a point at infinity for its complement.
So you say integral projective. What is integral projective?
Integral means there's a single irreducible component, and there are no nilpotent functions in the structure sheaf.
Projective?
Projective means you can embed it as a closed variety in projective space. Well, it's compact.
Complete.
Complete. Yeah, compact. So there will be non-compact things that appear also, for instance, C minus P. But we're not there yet. And so that's P. And then what is this? F. Maybe I should put it in a different order. So let me tell you what pi is. So pi, geometrically, you think of it as a map. You think of it as a map from a formal disk around 0. In the affine line, this has a coordinate. So roughly, I think of this as spec of formal power series in Z. If you know the difference between a formal neighborhood and that spec, ignore it. We'll come back to that. If you don't know, then this is fine for what I want to say. And then we also have the same thing without a coordinate, but I look a formal neighborhood of P in C. So if I choose a local coordinate, this would look like once I choose a local coordinate, this would look like some also formal power series here, where y is the local coordinate around P. So this would be a spectrum of this, such that I put a condition. So the geometric condition is this should look like it's a branch cover of some degree around 0. And algebraically, it means that if I pull back a formal function around P to here, I require that the ideal of functions that vanish at P, well, it maps here and generates some ideal, and I want that to be exactly the rth power of the ideal of functions vanishing here. So I require that functions pull back and vanish to order R. Okay? So geometrically, this is saying pi is a branched cover around this point of degree R. And this degree R is going to be also the rank of this vector bundle. So in Krichever's paper, he works with a local analytic coordinate, and then this would be like a map from, the usual map from a disk to itself that sends, just raises something to the power R. What's the best way to do this? Like this?
What's it? Sorry, what's your question about?
What's the best way to handle the boards?
Well, it says you wish it, I said, and I thought that's what's the best way to handle this data.
Yeah. Okay. Okay. So this vector bundle F is just a vector bundle or some torsion-free sheaf. So maybe on singular points of C somewhere else, it's not quite locally free. So this should be of rank R. And what do we do with this local coordinate? We want to compare, so the vector bundle has rank R. I could take, for instance, the structure sheaf here and push it forward. At the level of functions, that means just taking this and considering it as a modulo of this. And because the map has degree R, this is free of rank R over this ring. So I have to assume that this is an injection, and that takes the maximum ideal to rth power, and this will be rank R over this. More generally, I might like to look at functions vanishing to some order on here and then push them forward. So that will be where the n comes from. So phi is an identification. So I want to restrict F to this formal neighborhood of P, and I want to identify it with the push forward of the structure sheaf twisted by n. So this looks like what? This looks like z minus n kz as a module over this, which if I choose a local coordinate looks like k of y. Okay? So this here also has rank R. And I choose an identification. So if you like, I'm choosing a frame for this vector bundle in a formal neighborhood around P and identifying it with these functions which have pole of order n on the pullback. So this is the geometric data. And I want to explain how to get from this geometric data to this linear algebraic data. And I'll briefly say something about this relation. So before I do that, are any questions about the formulation of the data?
In your case, this n is arbitrary or
Yeah, it's part of, I should, let's see.
restricted by R or
Yeah, so I should, it's arbitrary. So I let R be a positive integer, and I let mu there's one more condition. I'll tell you where mu appears. These are arbitrary integers. So geometric datum of rank r, index mu, and level n is this following stuff. And where does, I told you what r is, it's a rank, and also a degree of a map. I told you what n is, just the order of some pole under this identification. And the mu, so f is such that, so mu is just Euler characteristic. It's the Euler characteristic of C with coefficients of f. So let me spell out what this is. It's the dimension of the space of sections of my vector bundle minus dimension of the first homology. Okay, so that's the condition on the vector bundle in terms of when you're studying moduli space of vector bundles, this kind of Euler characteristic often appears as a parameter. So you can, every vector bundle has a degree and a rank. And by Riemann-Roch theorem, you can relate degree, rank, and this index. Somehow this is encoding the degree of the vector bundle. So what is the idea of the construction? To go from geometric data to linear algebraic data. This is from geometric data to linear algebraic data. I have to tell you how to construct an algebra in one of these closed subspaces that's stabilized by it. And I'm going to construct that from this geometric data. So for simplicity, it's a little easier to think about, but it turns out not to matter what choice you make. So for simplicity, let's choose an affine open neighborhood of P, so that we can imagine we're just working on an affine curve. And then I want to look at functions on the complement. And I can express those in terms of functions on U that have possibly a pole of some order at P. So I can write that as the what do you call it? Direct limit. It's really union in this case of functions on U, but with poles possibly of some order. This is just that function on U minus P has a pole of some order on U. And I can do something similar for puncturing this formal neighborhood. So functions on.
Sorry.
Yeah.
Did you mean a pole at P?
Pardon? P is fixed.
Did you mean functions having some pole at P, at the point P?
Well, n can be anything. It can be positive or
Any
negative.
point.
N can be positive or negative. So it might also have a 0 or neither pole nor 0.
I'm not speaking about the order of the pole, but the pole is located at P,
Yes.
at the point P.
Yes.
But you wrote on U.
But P is in U.
P.
But formula must means poles at some other point of view.
It cannot have poles in U
I see.
otherwise at the point P, right?
So the way I've,
I'm sorry,
yeah, let me, so, just a minute. No, so I mean exactly a P. I do mean exactly a P, so to be more precise, let me write it like this.
okay.
Right, so what does this mean? This means, by definition, the notation, the traditional notation, would be that this is the ideal of functions vanishing at P. So the dual of that is O plus P. P is a point, so this would be O1 times P. This would be the dual. Like that. So I mean exactly at P. Okay. So likewise, I can do this on the formal neighborhood function.
So the poles can be only at this point. Одной точки.
I mean, this is the ideal exactly of things.
I think they ought to write a false or I think.
I guess it would have a priori. So if I have a function in here that vanishes at P, it might vanish somewhere else, but I don't care. So I'm on an affine. I don't care. The formula is sort of correct in that if I have a function here, maybe it vanishes somewhere away from P at some other point Q. That's possible, right? I could have a function on some affine variety which vanished at some other point. So I also want to see those. But those will also appear here among those things that have poles of some order at P. Okay. So I have a similar formula for a puncture formal neighborhood. And I want to compare these things. So I'm going to take, I can do this either for functions or for sections of F. I can compare its restriction to the complement, or its restriction to the formal neighborhood, or to the puncture formal neighborhood.
What is U? What is U?
UP was the spectrum of the ring of formal functions. So I can take a section here, I can restrict it to the complement or restrict it to the formal neighborhood, and then I can compare them on the punctured formal neighborhood. And the claim is that independent of U, I can express the cokernel of this map, the difference between functions on U and functions in the complement, in terms of the cokernel of this map. So we have restriction diagram that commutes, just restrict around the two different lines. And it induces an isomorphism of cokernels in the horizontal direction. I'll spell that out. say what it looks like in some local coordinates in a second. So this will be functions or sections. Functions or sections. F could be L. On U minus P, modulo those which were extended to all of U. Because this diagram commutes, there'll be a map. The claim is it's an isomorphism. One way to see that it's an isomorphism, well, you could choose U kind of very carefully so that you can really see it's an isomorphism. This is what is done in the Lasse's paper. Alternatively, you can express this thing in terms of local homology of P, which is independent of the neighborhood that you chose, and can be expressed in terms of formal power series. So there's an identification like this. And this is getting much closer to the kind of data we need in linear algebra. Because if I choose some local coordinate here, this is given by some power series, and this is given maybe by some Laurent series. Sorry, it looks like I got that upside down. Okay, I want to take some Laurent series modulo some power series. Okay.
Pardon me. On the upper right blackboard, in the left part of it, the last line, last two lines, inducing
An isomorphism of cokernels in the horizontal
in
direction.
horizontal. Oh,
Yeah, I mean, I could also look at it. I could also look at it in the vertical direction, but I need it in this direction. Yeah.
but may I ask, the horizontal in this diagram,
Yes.
the upper right arrow.
This one.
Yes.
Yes.
Is not it isomorphism if the dimension of U is greater than 1?
But we're on a curve.
Ah,
We're on a curve.
well,
So I do want to mention,
I
I do want to do higher
Okay,
dimensions,
okay.
but we're warming up to it. So in the higher dimensional case, you'll have some variety, say a surface, and inside that surface you'll have a curve, a divisor. And then P will get replaced with the divisor in that case. So yes, by Hartog's theorem, like the poles have to occur along a divisor, not in something of higher codimension. Okay. So in particular for F equals O, F is just the trivial bundle. I want to, we get the following. So I have this formal neighborhood of P. I have the functions there. Under my map P, I have a degree or a branch covered here, so I can pull that back from formal functions around 0 and the half-line line. That's my formal coordinate. So that's just power series in Z. This embeds into functions on the puncture formal neighborhood. Laurent series. This is where my Laurent series are going to come from. I could do something similar in this direction. Then there's a reduced map like this. And now, my algebra A is defined to be the image of on C minus P. So that's some affine curve. Now I'm thinking of P as a point at infinity. I'm looking away from it. I can restrict it to this punctured formal neighborhood. And then I can pull back under this branched cover. And so by definition, that's A. The theorem is going to be this A will be the kind of thing you want for this correspondence. And now I'll tell you what W is. So W is going to come from F somehow. Plus I haven't used the trivialization data yet. So what have I used? I've used the curve, I've used the point, and I've used the map P, but I haven't used the trivialization data yet. And the trivialization data is necessary for identifying a subspace here on which A acts.
Is it right that this here E in different terms is those Laurent series which can be extended globally to the curve?
They are, they're those that are pulled back. So I have this punctured neighborhood of 0 in the affine line. It has an unramified cover to a punctured neighborhood of P and C. And I'm asking for those Laurent series that are pulled back under this cover. So I can write that in words if you like.
And here, nothing yet related with this R, yeah? You have this R, positive number, which is,
It's more,
which is, as I understand, related to the reduction of Kp, and here it does not yet appear. Yeah?
it does not yet appear, but it will appear now when I talk about W. I mean, it appears implicitly because whatever this map pi is, it has some degree. It's degree R. So let me say in words what A is, and then R will appear, and then we'll go on to F, and then we'll see where this trivialization data appears. So so this here is a degree D cover. In a complex analytic local coordinate, it would look just like the R power map, say degree R cover. So this was minus P. This sits in C minus P. So A inside here, the Laurent series here, this is those that are pulled back from C minus P. Under this cover. And now I want to do something similar with the sections of F, but in order to identify that with some nice closed subspace of this, I'm going to have to use this trivialization data phi. So now for general F, or for the given F, the given F of rank R and Euler characteristic rule. Level n. We do the following. So again, I look at C minus P. So I look at sections on the complement to P. I restrict those to a punctured formal neighborhood. And then on the punctured formal neighborhood, using phi, I have an identification of this with H0 on, well, let me write it here again. So this is the push forward under this map of O n times P. And what is this module? So I can identify this. This is what? This is Z minus N times KZZ. So I have an embedding here. So this composite is going to be my W. And the theorem is constructive, so I'll tell you a little bit about the inverse construction. Where did it go? Did I rub it off? I'm afraid I rubbed it off, so I'll have to write it again. So this gives the construction of going from geometric data to this linear algebraic data. You have to double check that it satisfies all the conditions that we claimed. And the inverse operation roughly is the following. You use the filtration on the Laurent series. There's a filtration on Laurent series, as we said, just by order of pole. That induces a filtration on A and on W. This induces filtrations on A and W. We don't actually want them as filtered algebras. We take their associated gradients. And then there's a construction of Serre that goes from kind of graded commutative algebra to projective geometry. Takes the graded algebra to some projective variety, takes a graded modular of that algebra to some sheaf on that variety. And the claim is this get you back to where you started. So proj of GR of A will be exactly the curve. It'll stick back in the point at infinity.
I usually want to say
Maybe I mean Reese construction.
yeah.
So,
Yeah.
yeah. So let me say Reese construction. It's good because if Roma is around, you're not able to make it.
What is this construct? Reese construct?
Yeah, so there are two ways to associate a graded algebra to a filtered algebra. One of them is associated graded. One is to think of the pieces of the filtration as being connected by multiplication by some graded variable.
Some additional.
Yeah, you introduce a new variable of weight 1, and you define a graded module whose graded pieces are the pieces of the filtration together with this new operator that kind of raises 1 to the next. So this is called the Reese construction. And geometrically what it is you can think of a filter vector space as something that lives over the affine line that's equivariant under the dilation action. And this dilation action is giving this extra weight gradient.
that's what it's degeneration of the original battlefield is associated with.
So there's more or less a textbook way to go back. And then the theorem is that it really gets you back to where you started. And let me say one word about, here it is. Let me say one word about how you go from this linear algebraic data to something about ordinary differential operators. I'll be very brief because it won't appear again in the talk.
So this so your lower condition, what is AW is within double, yeah? No, this upper, yeah, this condition. So it's some condition of closeness, yeah? So where is it here in?
So here, in the opposite direction, I have a filtered algebra acting on some filtered module. By this Ries construction, I can turn it into some graded algebra with a graded module. And then there's a standard way to go from kind of graded commutative algebra to projective geometry. Geometrically, it's, like how do you get projective space? Well, you take affine space of one dimension bigger, you poke out the origin, you take the quotient. This quotient by dilation is giving the gradient.
There's a more nice way to say this construction is this correspondence is a possibility of suicide.
So I didn't quite follow, but maybe we can let it slide because I won't come back to projective geometry. Okay, so let me just say briefly one word about here because maybe from the point of view of mathematical physics, this is actually interesting stuff. So here the idea is that you, so from linear algebraic data, to ordinary differential operators. The idea here is you introduce, in fact, a larger ring of partial pseudo-differential operators. Some pseudo-differential operators and some other variable. So there's x and dx. They have formal power series coefficients. And we look at quotient by those that have start in degree with an x term in front of all the coefficients. So this gets identified with Laurent series in the inverse. In the inverse of this differential operator. And we set Z to be this formal inverse. So this is going to be the correspondence. And then the claim, and I think this, as far as I understand, is usually explained by construction of Sato. The claim is that there exists, given this linear algebraic data, a natural invertible pseudo-differential operator with some other conditions. S, so this is sometimes it's called Sato operator, such that, so if I identify this, there's a split. I can look at those with constant coefficients. So if I identify A as a subalgebra here, and then as a subspace there under the splitting, then I can conjugate A until it lives in the differential operators inside the pseudo-differential operators. So that's my commutative subalgebra. So there's, in the proof, you have to see where this operator comes from, but this is what's involved in the construction.
You see that these are differential operations.
So there's pseudo-differential operators which have the derivative with respect to x, but also some formal inverse of it. And inside of that, you have those that are actually differential operators. And the claim is that although you started out with some subalgebra here, under these identifications, it'll correspond to some, funny subspace of pseudo-differential operators, but there's a natural way to conjugate it to an algebra and actual differential operators. So this, all of this that I described is in a paper of.
Sorry, why do you speak about differential, pseudo-differential operators, not just polynomials or sort of functions of z minus to minus first? Why do you need operators at this moment?
Why do I need E or why do I need D? So what is D?
Polynomials of z
D is
of x.
D is generated by this. And this is some kind of completion of
So you need non-commutativity here.
What's that?
You need non-commutative algebra here, right?
It's this will be commutative, but it'll be a commutative subalgebra.
Yeah, yeah.
So the point is you're in some
Yeah.
problem. So you could start with the following. You start with your favorite ordinary differential operator.
Okay, but
Then you
but
look
it's-
for
sorry, finish.
then you're looking for trying to study its spectrum, or you're trying to find explicit solutions. So you might look for other differential operators that commute with it.
Mm-hmm.
And for the whole ring, subring of differential operators that commute with this one. For nice ordinary differential operators, that might be a fairly large algebra, giving something non-trivial. And then going back the other way, it's saying if you did that, you would get this linear algebraic data and then this algebrogeometric data. This will appear as the spectral data for the ordinary differential operator.
And when you speak about pseudo-differential operators, do you need smooth functions of?
No, this is all formal.
Or
This is all
series?
formal. It's just formal series.
Okay.
Okay. And you all know much more about KP than I do, but I should say that the interpretation of the KP equation in these terms, it's related to isospectral deformations of, if I start with this, a single operator, I look at things that commute with it, I get some subalgebra, and I want to write down deformations of that to preserve the spectrum. I'll get some system of differential equations describing that, and they will be encoded in some flow on this data. So that's the motivation as I understand it. I learned this from a paper of Motohiko and Nase, but there's also a paper of Siegel and Wilson that describes these things in more analytic terms.
Second name is Mulasse.
Mudlase. It's a Japanese name, I believe. This is Japanese. That doesn't look Japanese to me, but
I don't know.
Yeah.
But I know this name.
okay.
So this name usually not just
What's that? let me see how much time.
Japanese names usually don't use the letter F.
So this was supposed to be a way of motivation. The idea was that this might be something more familiar to the audience. I don't know if that succeeded.
Well, it's familiar, but not very well recognizable.
So the modest thing is to blame that not on Mulase, but on myself. So perhaps the paper of Siegel-Wilson would be more familiar, I'm not sure. Okay. So what one might like to do with this, so in higher dimensions, or in other contexts, these kinds of constructions where you want to decompose a vector bundle on some variety along some subvarieties with trivialization data becomes more involved. So in higher dimensions, Parshin Parshin School studies a Krichever correspondence of this sort. So for a surface, for instance, it tends to involve, say, a surface, a curve, a point on this curve, plus some torsion-free sheaf and some trivialization data. And they have a pretty good correspondence of this form that works in all dimensions, but the data becomes more complicated. In other contexts, you have something similar. So I want to discuss a topological analog of this. And this topological analog will be the way I want to think of the kind of right way to do this in all dimensions. By this, I mean sort of decomposition of a vector bundle with respect to some collection of subvarieties and trivialization data. So let me say a topological analog of decomposing a sheaf, I'll again call it F, with respect to subspaces. In some sense, this is much simpler. And part of the point of this talk is that when we come back to algebraic geometry and do this, it should look much more like the topological situation, which is simpler. So let X be some topological space. I don't care if it's algebraic or not. Fix a closed subspace. And its open complement. It's traditional to call the embeddings I and J for some reason. So for example, you might be in the plane.
X is instead of this Laurent series you had before. Yeah.
X would actually be the analog of C, the curve.
Of the curve.
Yeah, and Z will be the analog of P, and this will be the analog of C minus P.
Curve point and curve without point.
Yes, or maybe this formal neighborhood of P. This is too thin. In algebraic geometry, this will be too thin, so I'll need to thicken it up a bit. But in topology, this is just fine. So for example,
maybe X is P.
no,
Z
I mean exactly this.
And what is
Z is it's a closed subspace. For instance, a point in a curve.
UP denoted the formal name?
Yeah. So the point is that in algebraic geometry, if you just take a point and you look at what happens near a point, very little happens actually on the point. It happens in some kind of infinitesimal neighborhood of the point.
But, okay, if that is UP, what would be X?
C. So I have C, I have a point in C, and I have a formal neighborhood of the point in C.
Is that UP is that X?
You don't like thinking of UP as something closed?
Yeah.
Yeah, so think of it as a disk, a closed disk for now. I'll try to justify this.
Yeah.
Or just forget that I gave the first part of the talk and let's come back to topology. Okay. So now we're just doing pure topology. I have a topological space, a closed subspace, and its open complement. For example, the complex plane, the origin, and its complement. And then what can I do with the sheaf on this space with respect to these subspaces? Their standard ways to restrict and relate the sheaf to what it looks like on the closed subspace and what it looks like on the open complement. So given, say, a sheaf on X, say of abelian groups or vector spaces, maybe it's a sheaf of solutions to some differential equation, or maybe it's something, representation of a fundamental group. I can restrict it onto F and then include it back in. So I'll write it as F subset. And there's a map, a kind of restriction map in this direction. So I can take a section here and restrict it onto Z. And this fits in some kind of short exact sequence where I can restrict it onto the complement, and then I need to extend by 0 to get back. Okay, so there's a short, in fact, short exact sequence, or if it's a complex of sheaves, then it's some exact triangle. This will be, we have this one, and we also have the other direction. So I can restrict it onto U, and then I can push it back. And in this case, the pushing back is not quite exact. And what sits on the other side is some funny functor called I shrink. So it's whatever the right adjoint is to the push forward. So these two exact triangles give so-called rebluing data. The French word is refoulement. For reconstructing the sheaf in terms of these different kinds of restrictions. And I want to organize it in the following way. This is how it usually appears in textbooks, but there's another way to reorganize it, which makes it look a lot like, what was it? This kind of diagram. Not exactly that one, but the one where I had sections over U compared to sections, yeah, this one. Okay, so this is like the complement, this is like the closed, and this is the difference. So then I can repackage this as follows. So I can look at these two different restrictions, I wanted to put the closed one down here to match how I drew that diagram. Here's the open complement. And now I want something to compare these two, something that both of them map to. And you have to be a little careful. So if you think about it, this thing is really supported on Z, which is the complement to U. So if I try to restrict this onto Z, it will become 0, but the other way works. So let's see. The claim is that this square is the analog of this one. This commutes, and moreover, this one is the pullback along these two. So that follows by contemplating the exactness of these two sequences. So let me say this in words. I'm saying that any sheaf on a topological space that has a given closed subspace and its open complement, it can be reconstructed from the data of its restriction to the open part, to the closed part, and some comparison between them.
Could you please repeat?
Yeah, I'll say them. I said it, and now I'll write it. All right. So F can be reconstructed from its two restrictions. And a comparison between them. So if I only know these two things together with these two maps, then I can reconstruct F as the pullback. For instance, if I want to know what sections of this sheaf are, or what homology with coefficients in this sheaf are, I can compute it in terms of the same data here plus some long exec sequence. And there's a higher dimensional analog, which is less well known. So suppose I have two closed subspaces. I have a stratification. I could do this for actually any stratification, but let's stick to just two closed subspaces. Let's say this one is some Z1 and some Z0. Okay, and that's something I have to do. These are two closed subspaces. Then I can define strata. So let's see. So I like to think of this as Z2. So the top stratum will be X minus Z1. X1 will be Z1 minus Z0, and X0 will be Z0 minus, well, in this case, it's empty. So just Z0. So those are three strata, and then the whole space is the disjoint union of those. But that's not very useful. I need to know how they're related to each other in order to reglue things. So consider the inclusion of strata. They are subspaces, they're locally closed subspaces. Like that. And I want to consider a sheaf here, this restriction and pushback. And then I want to look at all the different ways to compare them. Okay, so define define a functor from, should really be complexes of sheaves because these functors won't be exact. So this will be defined as restriction onto the stratum and then pushing back. And the claim is that if I look at all the different ways to do this compatibly, I'll get some bigger diagram than a square. In this case, it'll be a cube. Yeah, so I can write it there. So we get for each sheaf F, I can look at these different restrictions back and forth to different strata, and I can organize them in a cube. So I want to draw it here because it's going to be a big cube. The composites of the phi k organize into a cube as follows. So down here, at one far end, I can restrict to the top stratum, go back, restrict to the next lower stratum, go back, restrict to the lowest stratum, and go back. And I can compare that to something where I just had two. So for instance, I could just restrict right away to the first stratum and then the bottom stratum, or to the top stratum and the bottom stratum, or the top stratum and the middle stratum. And over here, I could compare them. Let's see. Here I have, is this a 0? 1, 2, yeah, this is a 0. So we'll come in here. I want to take phi 2 out. I want that phi 2 here. So I could restrict to the top stratum and restrict further to the middle one or to the bottom one. And out here, looks like I have phi 0 on the outside. And phi, that's phi 0. This. And then back here, I have phi 1. So this is almost a cube. I'm just missing one vertex. The last vertex out here is F, and its comparison to restrictions to each of the strata. So just because the strata were given by maps of topological spaces, the diagram will commute, and the claim, if you like a proposition, as part of a more general proposition that we're working in a dimension, F is reconstructed from this diagram. And anything you want to compute about F can be computed from this diagram. For instance, the homology with coefficients in F. The precise sense in which it's reconstructed is that it's some limit of the punctured cube. It's the homotopy limit. Of the punctured cube. So this is a kind of construction actually that appears a lot in homotopy theory, taking limits of cubes. And what I want to explain now is why this doesn't work in algebraic geometry, and how you could make it work. So how much time should I?
15 minutes.
Okay, so we would like an algebra geometric analog of this, so that now I definitely broke it off. So that, for instance, in this construction in the Krichever correspondence where I had a curve, a point, I had these formal neighborhoods and the complements, and I somehow reconstructed sections of F and its homology in terms of the different restrictions, I would like to interpret it in these terms as somehow coming from a decomposition of the spaces. And I especially, on a curve, you can just do this by hand. You can make any calculation you want. In higher dimensions, it becomes more and more difficult. So I would like an analog of such a decomposition for vector bundles. For F, a vector bundle and these ZIs either subvarieties or maybe some kind of neighborhoods of subvarieties. It doesn't work. So the problem is the following. If X is, say, a variety, an algebraic variety, and U was a Zariski open, so for instance, X was my curve, and this was C minus the point. Then, instead of sheaves of abelian groups, my vector bundles live in some category of quasi-coherent sheaves, or coherent sheaves. There's a functor of restriction. It's perfectly nice. You can also push back, that's perfectly nice. But the other functor that I needed in these triangles right here, I'd like to say that F lives in some nice sequence like this. That's okay. However, this one is a bit of a problem. So this is okay. But here, what lives in the kernel of the restriction? It's not stuff, this goes back to Rosely's question. Why is it should be a formal neighborhood of P instead of P? If I have something that lives not exactly on P, but infinitesimally on P, maybe like a function which is not quite zero but is nilpotent there. And then when I restrict to the complement, it will die. And so that means the stuff that dies under restriction lives on the formal neighborhood. So this is some kind of formal neighborhood. So this triangle is okay. This one is not. It doesn't exist. So there exists this kind of exact triangle. This is just fine. If I interpret this correctly, living on the formal neighborhood. But this other sequence that I need in order to do the comparison this does not exist. And the basic reason is that this restriction, if it had a left adjoint, it would have to preserve products. It's a basic property of a functor that has a left adjoint. And I can give you a very simple example of what goes wrong. So for instance, on the affine line, if I look at a1 minus 0, and say we choose a coordinate here, t, so this is spectrum of kt. And this is spectrum of, well, I've deleted 0, so now I'm allowed to invert t. Then if I take an infinite product, say a countable product of kt's, and I restrict it here, in terms of modules, I'm just tensoring this with this module. And if the functor preserved products, I could move the Laurent polynomials inside the product. There's certainly a map to that. But this is not an isomorphism, because if you think of what is an element here, it's some sequence of polynomials tensored this. But because I tensor on the outside, anything that appears, it appears with a finite order pole. Where a sequence of Laurent polynomials, kind of the degree of the pole can go off to infinity in an infinite product. So this is all sequences of Laurent polynomials. There's no bound on the order of a pole that appears in the sequence. Where here, these are sequences of Laurent polynomials with bounded order of pole. So this is a basic problem. And what's going on is that whenever you see something like an infinite product, if you take it naively, you won't be able to move some tensor product through it. But if you somehow topologize it, for instance, in the product topology, and you complete the tensor product, then you will be able to do this maneuver. So the solution, this is the problem, the solution is to do some kind of topological algebra. And we already saw this in the first part of the talk, where we were talking about the Sato-Grassmann. There was this topology on the Laurent series, and we were only considering the closed subspaces on that. So this has implicitly been there the whole time. But there's a big problem with topological algebra. You can't really do homological algebra with usual topological algebra. You can try to do it, and it gets very complicated and technical, and still doesn't do what you want. And the basic problem you can see in an example. What's the basic problem with topological algebra? It should contain some nice topological abelian groups. It should also contain your discrete abelian groups, maybe your vector spaces. And if you want to do constructions in algebra, you want to take a map between two such things and look at its kernel and cokernel. But you know, for topological abelian groups, if you try to take a quotient by something that's not closed, often bad things happen. And one of the worst things that could happen, for instance, is you could consider power series in T with the discrete topology, or power series in T thought of as just a product with the product topology, or is that T-adic topology. There's a map between them. It identifies the elements. What is the cokernel? Looks like it should be 0, right? But this shouldn't be happening. You shouldn't have a map between two objects in your category whose kernel is 0, whose cokernel is 0, but it's not an isomorphism. It's a continuous map, but there's no continuous inverse. So that's the basic problem that makes naive topological algebra basically impossible. And so, however, there's a good solution to this problem. So let me formulate it as a theorem. Clausen-Scholze. It's a special case of a general formalism. So I'll state their theorem, and then I'll state our theorem. So they introduce various categories of topological modules in which you can do good homological algebra. So there's a good, and I'll give you a characterization of it and tell you how to compute it. So there's a good category. Good means, say, abelian, for example. Kernels and cokernels behave like what you think they should. I'm going to put them in quotation marks because it contains all your nice topological modules, but then new stuff. Approximately characterized by the following. You can characterize in these terms if you're careful. So one, it contains all discrete vector spaces, just usual vector spaces, as a full subcategory. So, well, all such things are free, right? They're just sum of k to have a basis. Those are not so interesting. However, you could take their duals. So if I take the dual of a sum, I get a product. How do I map out of a sum? I have to give you some big matrix. I can put any entries I want in the matrix, and they're indexed by a product.
The set I is finite or not?
Not necessarily. So I can be.
But what, then the view in what sense?
Dual in this category. So I
So
claim
we don't
there.
know.
I can construct it. I can construct it, but I think basically, I mean in general, right? In some mathematical problem, you construct something because you want to know it exists, but then once you know it exists, all you really care about is the formal rules for manipulating it. So I'm telling you how to compute in this category. Okay. So the claim is that there is a category, there's a notion of map between objects, and it has the property that if I map out of this to the ground field, I get this product, and it's the product in this category. So far, so good. That's true for usual vector spaces. And here's the new thing. Whatever this hom is, it's somehow continuous. So if I considered a product of vector spaces with the product topology and took its continuous dual, and we get back to where I started. So it's so hom is continuous. And even better, the tensor product is complete.
What you are saying is the content of the theory, right?
Yes, that there exists a kind of natural category
Okay.
with these good formal properties. It's more or less characterized by these properties. There's kind of a minimal way to do this. We get an abelian category in which
And
all,
I guess
all calculations work the way you
the
want to.
last applies also to direct sums.
It does, yeah. So nothing changes for the discrete vector spaces, it's only their duals that are known. But then there are other new objects in here. There are extensions that didn't exist before. So let me just,
Let's say in this your example, can you say what you should change? No, whether it's a fine line,
yes, I will.
what shall we change?
I'm going to tell you. Yeah. Let's see. Right. Okay. Right. Okay. So. Okay.
The last property was violated, right? As you explained, this last one was violated.
Yes. Yes. So I would say moreover, and it will explain why it works here now. So moreover, so let's call this category solid k-vector spaces. Let's call it sol k. And I can consider my polynomial algebra here. It's discrete, so just consider it here. But now I'm going to consider modules over it in this category, so they can have topology on them. So let me give an example of this sort, of what you do with this. Okay. So, there's a category of solid KT modules. It's a subcategory of all modules here. For which the generating objects are products of this. I could take different index sets. Okay. And there's an analog for any other ring or any other scheme. And then our theorem,
Generated in what?
meaning everything can be resolved in terms of those.
So it's like
So they play the role of the free
they play
modules.
the role of free modules.
Yeah. So the theorem, in a recent paper with your own Konovalov, is that working in this context, so I look at just usual commutative algebras with modules in these solid k-vector spaces of a certain type gives these kinds of decompositions. Topological type decompositions. With respect to, for any vector bundle, and much more generally, for any vector bundle on a variety, and with respect to any stratification, any reasonable stratification. And the stratifications can actually be very general. So you can consider, the one we consider, the most interesting one we consider is, it makes sense in this context to form a kind of skeleton of your variety, where in dimension k, you kind of take the union of all the formal neighborhoods at dimension less than or equal to k. This now actually makes sense as a geometric object here. And so I stratify the variety by dimension, where in dimension k, I look at the union of all formal neighborhoods up to that dimension. And if I decompose a vector bundle with respect to that, then I see some kind of these so-called adelic decompositions. So I can either stop there or...
Well, probably over, but can you say
Yeah.
what you should change in this?
Yeah, so let me tell you exactly what it looks like here. So in the example, the simplest case would say the following. I give you two versions. One is just with respect to a point and its complement, and the other is with respect to the skeleton. So with respect to a point and a complement, it says that I could put, well, on a line, there are no interesting vector bundles. They're all trivial, so we might as well take the rank 1 trivial one. Right, so on the complement of 0, I have round polynomials. Here, instead of the point, and instead of the formal neighborhood of the point, I have power series. That turns out to be the complement of this, where this is understood in the topological sense, or as an object of this category, solid abelian groups. This is topological. So I drew it backwards. This is I. And this is the open complement, which is the function I found. And then what fits here is the Laurent series in T.
And the topological, no, the up there, right? In the word topological, that you should go up there.
I see. Yeah. And let me just write the analog of this for the adelic analog. And this was, for curves, a statement like this was first proved by Andre Weil. So in that case, it would say, here, on the closed part, we would see the product of all completions at all maximal ideals. So if it's an algebraically closed field, I complete a, T minus lambda for every scalar. So I'm looking at the formal neighborhood of every point in that fine line. And over here, I would have the function field.
What does the inverse check sign mean?
Completion. So these are like formal power series, Taylor series centered at lambda. Formal Taylor series at lambda. So you could do this actually on any curve, not just that fine line. You can put any vector bundle here. You can reconstruct it from the collection of all its completions, what it looks like over the function field together with a comparison. So this was known to Andre Weil. There's a higher dimensional analog done very axiomatically and formally by Parshin and Beilinson. And the goal of our paper was to kind of do this in all dimensions in a very geometric way, getting it as a consequence of kind of new locality using these naturally topologized modules. So I'll stop there.